All right, so let's talk about the resolvance of the resolving power of diffraction gratings, right? So let me just explain what it is, and then I'll explain why the formula is the way it is, right? So let's look at this spectrum here, okay? Let's imagine that there's actually a spectral line that's really close to this blue line here. And we're trying to decide whether it's one line or two lines, right? So you got this line here, you got this line there, right? This corresponds to a difference in the wavelength, right? And so the question is it one line or is it two lines, okay? And if you have the adequate resolvance, then you can do it, and if you don't, you can't, okay? So anyway, that's what we're talking about, right? Is if you have one spectral line in this spectrum here, right, that's really, really close to another spectral line, okay? Can you distinguish that it's two lines, or does it just look like one line all blurred together, right? Okay. So what they do is we talk about the resolvance. So this is the difference in the wavelength. So it's actually the distance separating this thing. Okay, remember that this is all spread out. This is what n lambda equals d sine theta, right? So this is on a screen. We've projected these spectral lines, right? And these distance here correspond to a difference in wavelength, right? Notice that it's per wavelength, right? So the way this is set up is, let's say your resolvance is 1,000. Okay, you can discern one part in 1,000. So if you've got 1,000 nanometers, you can detect something that's 1 nanometer apart, right? Now, if your resolvance is 10,000 and your wavelength is, say, 1,000 nanometers, right? Okay, then you could resolve 1/10 of a nanometer if you had an R of 10,000, right? And so on. Okay. Now, why is it this way? Well, this one's easy to explain. That's the order. Okay. So you have the first order, you have the second order, right? Okay. You've got the order of the phoenix, obviously, right? But anyway, here's our first order here. If you look down here, notice that the second order is twice as spread out. Look at this distance. This is the second order. Here's our first order. That's because of geometry. Okay. So the second order gets more spread out. So therefore, if you're looking at the second order, you would have twice the resolvance. So we put that in there, right? And then this N there, that's the number of slits illuminated, right? Okay, it's not the number of slits you have, it's the number of slits that get hit by the narrow beam of light. So if you've got this bunch of slits like this, right? Okay, and then you've got a beam of light like this, well, you've got 1, 2, 3, 4 slits illuminated by this laser light, okay? So that's, you gotta keep that in mind, right? Okay, now why is that the case? Okay, without going into differential equations, it's because of this, right? That as we get more slits, these things get more distinct, okay? These guys get more distinct as you get more slits. And that's because there's more overwhelming destructive interference when you don't have, there's always going to be some slit that's going to destructively interfere at these distances in between. And you really start to only get the constructive interferences and exactly the constructive interferences. And really it's limited. If you have 100 slits, then you're going to get, it's going to be 100 times the attenuation, more or less, right? Okay, so let's look at an example problem here. This really is a fairly simple problem to solve, right? Okay, so a diffraction grating is used to resolve the two lines in the spectrum of sodium in the second order. So the two lines have wavelengths of this and this, right? So the first thing I'm going to do is I'm going to figure out the difference in the wavelength, right? So the difference in the wavelength is going to be 589.592 nanometers, right? Minus 588.995 nanometers. Let's figure out the difference. I can always do that. I'm always good at subtracting, even at the end of the day. 589.592 minus 5, whoops. I said 5, but I typed a 2, 0.995. All right, here we go. All right, so this is 0.597 nanometers is the difference, right? And then what do we use for the wavelength? Do I use this one or do I use this one? Okay, and the answer is if they give you two wavelengths, use the average, okay? So 589.592, right? Plus 588.995. By the way, you'll get almost exactly the same answer if you use either one of these because they're so close together. But I'm doing what IB did in their mark scheme, okay? Now let's see, am I so lazy that I'm going to go and put a plus between those two numbers? Yes, I am that lazy. I am that person. Oh, Oh, no. Oh, wow. 995. No, I didn't make a mistake. Oh, this is good. I thought I'd made a mistake. Okay. Okay, here we go. Sorry about the dramatic pause there. Okay, so 589.2935. Okay, that is our, okay, so there we go. So now we've got our wavelength in that, right? And then it says enable the two lines to be resolved, but we're going to do it in the second order, right? So our M is going to be 2, right? So now we're all set. So our R, which we really don't care about, we never have to calculate it, is the wavelength. So 589.2935 divided by the difference in wavelength, so 0.597. By the way, you'd want to put all of this stuff in that box. I just didn't want to do it. Okay. And then that's going to equal 2 times N. All right, that's a 2, not a Z. 2 times N. Okay, I think I can do this. So I'm going to take that number divided by the difference, and then I'm going to divide it by 2. And I get that N is 493.5. I think we do have 3 sig figs, so we can say 494 slits. Ta-da. All right, there we go.